All right, so if you recall from Wednesday we were talking about solution concentrations, and we ended with the concept of dilutions. That is the lowering of concentration by adding more solvent. And so we went through the process of identifying some key terms with regard to dilution, stock solutions, standard solutions, and then we gave you an equation for calculating dilutions. And in particular, this equation is especially useful for making solutions. So if I have a stock solution, I want to make a diluted solution, how much of the stock solution do I need to make? How much of the stock solution do I need to use? And then we did an example. Today, we're going to focus on chemical reactions again. And particularly relevant to this week, we're going to talk here about titrations. So hopefully from your lab, you already know a little bit about this. Titrations are analytical techniques where we use the concentration of a known sample to figure out the concentration of an unknown sample. Titrations are sometimes referred to as volumetric analysis. Because ultimately, what we are doing in comparison is we are comparing volumes, essentially. Volumes and concentrations in particular. This is different from gravimetric analysis, which, if you remember the empirical formula lab that we did about a month and a half ago, that empirical formula lab focused all on weight and on mass differences to figure out, okay, how much copper do I have? How much sulfur do I have? Or whatever the case may be. Here we're using volumetric differences, and that's why this is called a volumetric analysis. Now, there are two different terms that are used for describing the ultimate end of a titration. The first of these is called the equivalence point. Now, the equivalence point is technically what we are shooting for. That's when we have equal amounts of our acid and our base, if we're doing a neutralization, or equal amounts of our two reactants if we're doing some other kind of titration. In 2 weeks, you'll do a redox titration using vitamin C. That one's not technically acid-base, but it still has an equivalence point. There's a spot where the amount of vitamin C and the amount of the other titrant are equal to each other from a molar standpoint. Now, equivalence point is generally difficult to see. So from an analytical standpoint, what we tend to focus on instead is something called the endpoint. The endpoint is when we do a titration and we use an indicator. The endpoint is a visual cue caused by the color change of that indicator. In lab this week, we used phenolphthalein as our indicator. Phenolphthalein is colorless in solutions up to around pH 8 or 9 and pink thereafter. We were using that as our endpoint in that particular case because it was close enough to the equivalence point that we can make a really, really strong estimate off of it. Now, there are better, more analytical techniques that can be used. And if you take Chem 106, we'll get into more of those kinds of techniques there when it comes to how to do this kind of thing on a more precise kind of level. But for most cases, and even in professional laboratories, usually the endpoint is good enough. And we can use that endpoint to determine the equivalence point and therefore the concentration of the other solution. A little word here on indicators. Indicators are usually some sort of commercial dye that, based upon changes in pH, will gain or lose hydrogen ions. And the gain or loss of that hydrogen, process called protonation and deprotonation, will cause the dye to change color. And so what we see in phenolphthalein is that particular color change results in going from colorless to pink. In other cases, we can see transitions from orange to red, from blue to green to yellow. There are lots of different variants. There are lots of different kinds of pH indicators. The one we tend to use the most often is the phenolphthalein. And the reason behind that is phenolphthalein, because its equivalence point is so close to neutral pH of 7, it does a pretty good job of estimating those kinds of neutralization reactions, and is actually useful for neutralization reactions that actually have equivalence points slightly higher than pH of 7, which is pretty much the case for any weak acid like acetic acid. But for other kinds of titrations, phenolphthalein is an inappropriate indicator because it doesn't change color at the right spot, and that's where these other indicators would come in. So before we move on completely, let's talk a little bit about solution stoichiometry. Now, titrations represent a very specific type of chemical reaction that occurs in aqueous solution. In particular, we're talking usually about a redox reaction or some kind of acid-base neutralization reaction. But for other kinds of reactions, a titration isn't going to be the most appropriate form. For example, a precipitation reaction. A precipitation is not going to really do a whole lot as far as titrations are concerned because you've got that solid that's being formed along the way. And if I want to estimate how much solid is going to be present, I'm not going to go to a titration to do that. So I want to bring back an old concept here. We draw this one straight out of chapter 7. This is our mole map. Remember, we talked about this when we talked about limiting reactants. Essentially, we've got a group of conversions on the left-hand side, a separate group of conversions on the right-hand side, and that wonderful old bridge from the balanced chemical equations linking them together. Well, one thing that we can add is this tends to work really good if I have solids or gases, things that I can measure masses of and be accurate. Pure substances. Solutions, however, aren't pure substances. In fact, most of the mass, most of the volume in a solution is from water, and the water tends not to react in the equation at all. So how do we account for that? Well, that's where that concept of molarity can come in. By using molarity, I can take a solution containing A in liters and connect it to the number of moles in that solution. And same thing for the other side. I have a solution of B in liters and using molarity, I can connect the liters and the moles. How do I do that? You have to remember our equation. Molarity is moles of our substance over liters of solution. So manipulating this equation, molarity times liters would give me moles. Or moles over molarity would give me liters. So technically, these arrows can go both ways. So from this perspective, everything we did in chapter 7, as far as limiting reactants, stoichiometry, all of those rules still apply. The only thing that's different is we now have another way of getting to moles. And when we do gases in chapter 10, there will be another way of getting to moles that would allow us to do stoichiometry in the gas phase as well. So keep this image in mind as you're working through. One thing that is important for us, though, if we are doing any kind of solution to solution calculation, there is a shortcut that we can use. So any kind of titration, like the ones that we just did this week, instead of going through the normal stoichiometry rigmarole of doing that series of 3 conversion steps or whatever it is, since we're going to end up going from volume to volume or molarity to molarity, we can use that to our advantage. And that's where this equation comes in. This is our titration equation. Our titration equation should look familiar. If I take this part off on the bottom, what you have is basically the dilution equation. Molarity times volume is equal to molarity times volume. The only difference is that in the dilution equation, because the number of moles don't change, I don't need to account for moles at all. In the titration equation, because I'm dealing with a balanced chemical equation and I'm dealing with 2 different substances, I have to know the relationship between those 2 substances in that balanced chemical equation. And that's where these values come in. These are the stoichiometric coefficients found in the balanced chemical equation. So in a lot of cases, at least for acid and base, 1 or more of those is usually 1. In the titration that you did this week, acetic acid with sodium hydroxide, those reacted in a 1-to-1 ratio. So in that case, the denominators were both 1 in those cases. Makes the math really easy to follow. But if you had a situation like this one, where the ratio was not 1-to-1, forgetting this denominator step would absolutely mess up your calculations. You could not get the correct answer. In fact, you would end up getting off by a factor of 2, which can be pretty devastating if you're trying to measure things out and estimate. So imagine you did this and you're trying to use the data to figure out, okay, how fast can I do this titration? If the titration is supposed to take 30 milliliters, I'm not going to sit there and flick my wrist 635 times to get 30 milliliters. I'm going to open that thing up, let it flow down for 20, 25 milliliters, and then I'm going to fine tune it once I get close. Well, if I'm wrong about that calculation, my calculation says it's going to take 30 milliliters and ends up taking 15. What happens when I get to 25? The data is completely useless. I have to start over again. Calculations do matter. You got to make sure that you get it right. And so that's where these coefficients are going to play a significant role. So again, any kind of calculation that involves solution to solution, we can use the titration equation for. I know it says acid and base as those indicators. We can just turn these into A's and B's and be fine. Molarity times volume over coefficient for reactant 1 is equal to molarity times volume over coefficient for reactant 2. Now, usually we think of titrations as acid and base, but again, it doesn't have to be that way. And if I'm going from solution to solution, I can take this particular shortcut and work out okay. All right, let's do an example. What is the concentration of sulfuric acid if 15 milliliters of it reacts with 18.45 milliliters of a 0.0973 molar sodium hydroxide solution? Okay. I'm going to pull that equation I wrote back up because it is the exact equation that is being asked for here. Since this is a titration, since we are talking about a calculation here, involving one solution being compared to another, I can use the titration equation. Remember the titration equation, M1 V1 over N1 is equal to M2 V2 over N2. For our purposes here, we'll make 1 the H2SO4, we'll make 2 the sodium hydroxide. Now we just need to plug in the correct values in the correct places. We don't know what the concentration of the sulfuric acid is, so that's what we're trying to find. We are told that we have 15.00 milliliters of it, however. And we know that the coefficient for it is 1. On the opposite side, our concentration is 0.0973 molar. Our volume is 18.45 milliliters. Notice when I'm using the titration equation, I do not need to turn the volumes into liters. Since this is not a stoichiometric, it's not a unit cancellation kind of dimensional analysis problem, all that matters is that I use the same unit on both sides of the equation. So my concentrations have to be the same unit. My volumes have to be the same unit. So long as they are consistent, it doesn't actually matter what they are, which really comes in handy. Again, if I'm given percent by mass, for example, I can plug that in directly. I don't have to convert it to molarity first. Coefficient for the sodium hydroxide is 2. Solving for molarity, I've got 0.0973 times 18.45, divide by 2, divide by 15.00. To 3 significant figures, I get a molarity of 0.0598 molar sulfuric acid. And again, since I'm dealing with a solution here, I have to make sure that my unit both includes the concentration unit, molarity, and the solute that is being described, the sulfuric acid. If I don't have both of those things, then I have an incomplete answer. I need to know what the concentration unit is. I need to know the solute that that concentration unit describes. All right, any questions with example 15 here? All right, let's look at example 16. What mass of sodium hydroxide is needed to precipitate the cadmium-2 ions from 35 milliliters of a 0.500 molar cadmium nitrate solution? Okay, even though we usually think of sodium hydroxide as a solution, we know that in this particular case, we are not going to be able to treat it as such. And the reason why, we're asked for a mass. So this is an example of where we need to use solution-based stoichiometry to figure out our nature here. The reaction here, from a net ionic perspective, I've got cadmium-2 reacting with 2 hydroxides to make cadmium-2 hydroxide. How did I know that that's what it was going to be? Well, it's kind of putting together the pieces. The true reaction, we could draw this out. Cadmium 2 nitrate and sodium hydroxide yields cadmium 2 hydroxide and sodium nitrate. We could have gone this direction as well. It would have been just as fine, just as good. All of the coefficients would have worked out the same. And so in this case, it really doesn't matter. If you kind of were able to see the net ionic equation there, you could have run with that directly. You had the tools to figure out the balanced chemical equation based on the 2 reactants, sodium hydroxide and cadmium 2 nitrate. So we can't use the titration equation here. We're going to have to go kind of the long route. The long route is I've got a volume of cadmium and a molarity of cadmium. And if I put those together, I would get moles of cadmium, which I could then turn into moles of sodium hydroxide and grams of sodium hydroxide. Now, from a stoichiometry, from a dimensional analysis perspective, there are a couple of ways that we can go about this. And again, it kind of comes into your level of comfort with dimensional analysis. Me, I like to put everything in dimensional analysis if I can, because that means that I can do all of the calculations in one blur. And to do that, what I have to understand is if I start with my volume, molarity is a definition. Molarity says that there are 0.500 moles of cadmium nitrate in 1 liter of solution. Well, if I know how many liters I have, that's a conversion factor right there. Any fraction can be used as a conversion factor. I just need to flip it in whatever way is necessary to get it to cancel out the units the way I want to cancel them out. So if I take that perspective on, all I need to do to use this as a conversion factor is to get this milliliters into liters so that it'll properly cancel out, give me the moles that I want, and then I can use the rest of the balanced chemical equation to get me the rest of the way there. So 35 milliliters is 0.0350 liters. So I'm going to start with 0.0350 liters of cadmium nitrate solution. For every 1 liter of that solution, I get 0.500 moles of cadmium nitrate. My balanced chemical equation says that every mole of cadmium nitrate will give me 2 moles of sodium hydroxide. And then 1 mole of sodium hydroxide. Looks terrible. One mole of sodium hydroxide. Need a molar mass. 22.99 for sodium, 16 for oxygen, 1.01 for hydrogen, and even 40.00 grams of sodium hydroxide. Make sure all my units cancel. I have liters of solution, they canceled. I have moles of cadmium nitrate, they canceled. I had moles of sodium hydroxide, they canceled. Only thing left is grams, which is a unit of mass of sodium hydroxide. 0.0350 times 0.500 times 2 times 40 divided by all ones in the denominator to 3 significant figures, 1.40 grams of sodium hydroxide. So that's what it would take. It would take 1.40 grams of sodium hydroxide to get this precipitation to occur. So much of what we did there is the same kind of stuff we did in chapter 7. There's just that one extra little wrinkle. That extra little wrinkle of how do you get to moles so that you can cross that bridge. Molarity times volume is that direction. But you can use that molarity as a conversion factor if you don't want to do a separate calculation step, which I always advise doing as few calculation steps as possible. Any questions here? Number 16. All right, number 17. I want you to try this one on your own. If it takes 21.33 milliliters of a 0.1199 molar sodium hydroxide solution to reach the endpoint of a reaction with 25 milliliters of an unknown concentration of hydrochloric acid, what is the concentration of that hydrochloric acid? So take a couple of seconds or minutes rather, and try to work through this and see what you come up with. I'll come around and kind of check your process, see if you're going in the right direction. But go ahead and start. Okay, most of you are on the right track. This is the process that you want to go through. So I saw some of you were going through and doing the dimensional analysis kind of process. That will always work. That'll always be there in your back pocket. But what I want you to recognize is that in the circumstance where we have two solutions, two volumes, two concentrations, it's way easier to go the dilution or the titration equation route than it is to go the dimensional analysis route. You can do it, but it was going to take you a lot longer to get there. And in that last step, what you would have ended up doing is you would have had moles of hydrochloric acid and milliliters of solution. You would have had to divide those two to get to the molarity. So going that route, the dimensional analysis route, it would have been a two-phase calculation route. You would have done the stoichiometry to figure out the moles of hydrochloric acid, and then you would have put that into the molarity equation to figure out the molarity of the solution. All right, any questions here? All right, one more. Again, try this here on your own. As a little bit of help, I'll give you the balanced equation as a starting point. We've got calcium hydroxide reacting with perchloric acid to make calcium perchlorate and water. All right, so try to figure this one out. How much of the perchloric acid do you need to neutralize 50 grams of the solid calcium hydroxide? So this will be our last problem. Anytime we get into solution-based stoichiometry, the problems are going to be more difficult than titration. The idea of organization is really what's important here. If you can get yourself organized, you can go a long way to making sure that you got the right thing. So recognizing that you're starting with a mass of calcium hydroxide, I can turn that mass into moles. I can turn the moles of the calcium hydroxide into the moles of the perchloric acid. And then the last step here, going from moles to liters, that's where that molarity came in. Again, you could have stopped there, used the molarity equation to figure out your liters, or use the molarity as a conversion factor like I did. Either way, you'd end up with 11.7 liters of this particular acid solution. Why so much? Well, that's a lot of calcium hydroxide, and the solution's pretty dilute. So it would take a lot to neutralize it. We would need a much more concentrated sample for this. Okay, remember, review on Monday. We'll do some more examples. Bring your own questions to it. It'll help the review a lot if it's driven by your questions rather than what I think you don't know. Have a good weekend.